So here's an example. So here is our thin planar element. It's subjected to stresses as shown. 80 MPa. That's the same as 80 MPa. I just won't write it down. 50 MPa in tension. Same 50 MPa on the other side. And then I'm going to show some shear stresses. And they are 25 MPa. Okay, maybe I'll just write down the other one. So 80, 50 MPa, 80 MPa. Okay, the questions are: one, draw the Mohr's circle. 2, find the principal stresses. 3, find. So let's do one thing. Let's find the principal stresses and their direction. And then find the maximum shear stresses and their direction. So pretty much everything what we talked about so far, but using Mohr circle. Okay, so one way of doing this, if the first line said there was no question on Mohr circle, is you can take the equations, plug the values in, and you will be able to solve all those things. But I think the Mohr circle is a much more powerful way of doing this problem. So let's use the Mohr circle method. Okay, so all I need to draw the Mohr circle is center and the radius, right? Because it's a circle. So let's do to compute that. Before we do that, let's just write what the sigma x, sigma y are. Sigma x, so our normal element is like this. Okay, so going by that figure, we can see that sigma x is minus 80, right? A normal stress element has tension or tensional stress, while we have compression, the 80 MPa. And then sigma y is in the right direction, so it's 50. And then tau xy, if you see our convention is counterclockwise positive. So here we have clockwise. So I'll just put negative 25 MPa. Okay. So that's just translating what the problem is given to our language, the convention we used. Now let's start drawing the Mohr circle. So center. The center is sigma x plus sigma y divided by 2, 0. And that is minus 80 plus 50 divided by 2. It's, I think, minus 15. And then the radius is sigma x.
Wait, minus 80 plus 50? Wouldn't that be like negative 30?
Divided by 2.
Oh, right.
Yeah. Sigma x minus sigma y divided by 2. Square plus tau x y. Okay, so square root of minus 80. Get the formula right. Yeah, sigma x minus sigma y is 50 plus minus 25 square. Okay, it's 69.625. Continuing from where we left last time, we were talking about Mohr Circle, how to use Mohr Circle to find the principal stresses and maximum and minimum shear stresses. So here is a problem based on Mohr Circle. Okay, so that cube element is subjected to stresses as shown. We've got to draw the Mohr Circle, find the principal stresses and the direction, and then find the maximum shear stress, maximum and minimum perhaps. Shear stresses in the direction. And so we need to take what we have over there and translate into variables of interest which were used in our derivation. So sigma x is the stress in the x direction. You can see that it is compressive. So I put a negative sign, so minus 80. And then the the normal stress in the y direction is tension. So it's 50 with a positive sign. And then the shear stress, the way we look at the shear stress is if it leads to a clockwise rotation at face A. What is face A? This is face A. Then we would put a negative sign, and that's why I put a negative 25 MPa. Okay, so this here, what I've drawn here is how we had defined our shear and normal stresses, so that you can use this figure if you like to understand the signs going into these variables. Okay, so then we can find the center, which is simply sigma x plus sigma y divided by 2, which is minus 15, 0. And then the radius of the Mohr circle is given by that formula, and that comes to 69.625. Okay, so now let's proceed to draw the Mohr circle. It's basically, once you're at the center, once we have the radius of the circle, we pretty much can draw the Mohr circle. So I need to move the circle such that its center is at negative 15, 0. So I just moved it slightly to the left of the y-axis. And so let me put that point down. So it's the center minus 15, 0. And then this radius is 69 point, I think 6 or 69 point. 69.6. Okay, so if I ask for the Mohr circle, that's pretty much what you need to draw. You don't need to do more than that, right? So that answers part one. Okay, part two. We want to find the principal stresses, right? So principal stresses are this point and this point, which is, well, since we know the radius of the circle is 69.6, it's easy to see that this point here is going to be the radius minus 15. So let's call that sigma 1, 0, sigma 2, 0. You can see that sigma 1 is simply 69.6 minus 15, just by looking at that figure. That radius minus the distance of center from this is going to give us the principal stress. And then sigma 2 is 69.6. So this distance is 69.6. So I need to do minus 69.6 minus 15. So one of them, well, it's minus 84.6, and then the other one is 54.6 MPa. So this we arrived from looking at the figure, right? We didn't have to do any math to get that. Well, we did have to do the addition, of course, but we didn't really have to write those complicated formulas. Okay, then the shear stress, which is going to be right here. Yeah, we know that it's clearly the radius of the circle, which is 69.6. So tau max, or rather this is minus 15 comma tau max, right? Minus 15 being the stress there, and that's going to be minus 15 comma tau min. You can see that the tau max is minus tau min equals the radius, which is 69.6. So this actually solves part 3, which is the maximum stress. Okay, so now there's some other things which are not part of the question, but I think I should do it so that way you get a better idea of what the Mohr circle does and what other information can provide. So I'm going to copy this figure in the next page and then show you some more things, and also compute the direction of the principal stresses in a bit. Let's copy this. Okay, so let's draw the stresses on the two faces in this figure. So we had drawn the cube. The cube had stresses in the negative direction for sigma x. We had a positive stress in the y direction, that's 50 MPa. And then we had shear force acting downwards on face A. So this is face A, and that's say face B. So A and B. Okay, so let's just draw what that face A is on the Mohr circle. So first thing to note is that there is a compressive stress of 80 MPa on face A. And then the second thing to note is that the shear stress is 25 MPa, and it is clockwise. So clockwise is negative for the cube, but negative shear stress shows up as positive shear stress on the Mohr circle. So at A, on Mohr circle. So let me just put Mohr circle. The coordinates of A. So I need two things, right? Sigma x and so sigma and tau to draw it on the Mohr circle. So A, the stress is minus 80 because it's compressive. And then the shear stress is, as I said, that 25 there is clockwise. So it's negative for the cube. But when we draw it on the Mohr circle, it's going to be with a positive sign. So I need to put 25. So if I draw this on the Mohr circle, it will be, since sigma 2 is 84, it will be very close to somewhere here. Just put it here. So that will be A. So then we can look at B, which is this thing on top, the surface on top. So stress on B is 50. Right? And then the shear stress is, as you can see, it's counterclockwise on face B. So counterclockwise for the cube is positive, but when we show in the Mohr circle, it's going to be negative. So I put it with a negative sign. So it'll be the point 50. So it'll be close to here. And then minus 25 is exactly mirror of the y coordinate of A. So B, and then I can join that if I need to. Okay, so now let's try to figure out what the principal directions, the direction of principal stresses are, sigma 1 and sigma 2. So this will be two, continuation of two. So let me call that 2b. Maybe I can call the first part as 2a. Let's go here. This is 2a. This is 3a. And then the direction will follow here. Okay, so I need to find the direction which the angle made by the principal stress with the face A. Okay, that's what I'm after. And this can be easily obtained from the figure. You can see that the angle made by A with principal stress sigma 2 is going to be this way. So that's in our notation, it's 2 phi S2. Sorry, 2, my bad, it's P2. S is for shear. So 2 phi P2. And then if I want to find the angle made with principal stress 1, I'll have to go all the way to here. Let me just raise this center for a second. So I need to go all the way here, all the way there. So 2 phi P1. Okay, so what I recommend is just try to find the smaller of the two angles, and then all you need to do is add 180 degrees to that one to get the second one. So phi P2 is 2 phi P2 is acute, which is less than 90 degrees. And so I can find that by using trig. It's basically the, so if you want to find phi, then you can see that this is the radius, 69.6. And then the side here is clearly at 25. So I can use sine of 2 phi P2 equals 25 divided by the radius. And I'm just using trig to do this. I could use the formula, of course. It's no, this is 1 and this is 2, just because sigma 1 is
2b.
It's 2. because I'm finding this angle here. Do the math on this. So it comes out to be 21 degrees. So phi P2 is 10.5 degrees. If you want to find phi P1, so 2 phi P1 equals 180 minus 2 phi P2. You can just observe that from the figure, right? They are 180 degrees apart. Sorry, my bad. It's 180 plus, right? Not minus. So that comes out to be 201 degrees. So phi P1 is half of that. 0.5, I think. Okay, and then finally we need to find parts 2C, which is the angle made by maximum shear stress, 2C, or sorry, 2, it's 3B. Yes, I'll draw the angle in the figure, then it's easy to compute that. So this is the angle made by face A with the maximum shear stress, right? So the maximum is here, minimum is there. I need to go this way. And so it's going to be 2 phi S1 because that's the maximum shear. And to find the minimum, I need to go very cluttered, like this. 2 phi S2. So again, you can use trig, right? You can see that this is R, and then if I want to find this angle, then okay, the easiest way seems to be that the angle made by 2 phi S1 and 2 phi P2 is 90 degrees. So it's clearly going to be 90 minus 2 phi P2. Right, you can see that this angle is 90 degrees. And so I just need to subtract 90 from 2 phi P2. So 2 phi S1 equals 90 minus 21 degrees. Which is 69 degrees. However, one thing to note is that the way I view this is it's clockwise, right? And clockwise is negative. So I need to put the sign there. So that's minus 69 degrees. Okay, and then phi S2, okay, which you can see from the figure, it's basically 2 phi P2 plus 90 degrees. So this is 90, and then that angle. So 90 plus 2 phi P2 equals 90 plus 21. Yes, that's right. Good catch. Yeah, 2 phi S2. And so from that, we can find phi S1, which is a minus 34.5 degrees. And then phi S2 is half of 111. So that's 5.5 degrees. Okay, so we can also draw what the cube will look like when we rotate it by an angle equal to phi S1 and phi P1. Let's just do that quickly, and we're pretty much done. Okay, so here for phi P1, we need to rotate the cube by an angle of 10 degrees. So anything which is twice on the Mohr circle has to be, anything on the cube is twice that on the Mohr circle. So we always have to divide it by half. So let's draw the cube when it's rotated by 10.5 degrees. Okay, so that face A, sorry, the face C, phi P2. Yeah, so face A is rotated by an angle of 10.5 degrees. That angle is phi P1 or phi P2 equals 10.5 degrees. So once we rotate this, now we need to draw the maximum, sorry, the shear and the normal stress on this plane, on this cube. So what we see here is when it's rotated by 2 phi P2 on the Mohr circle, the stress is sigma 2 comma 0, which means that the shear stress is 0 and the normal stress is sigma 2. And sigma 2 I wrote down earlier, I think it is. Sigma 2 is minus 84.64. So what I do is I'll draw those stresses on face A. Actually, you know what? I should write it as 84.64 with the positive sign, only because I'm actually showing the compressive force already on the figure. So that's the convention. You show the right direction on the figure, compression, then you don't put it as negative. If you show it at tension, then yeah, you need to put negative. And then on face B, we would have the stress of sigma 1, which is now, see, sigma 1 was 54.64.
Got the 4 on the top.
54.6. Yeah, so that's on when it is turned by 10.5 degrees, there's no shear stress, there's only a normal stress as shown. Okay, now we can do the second part, which is show what happens when you rotate the cube by 34.5 in the clockwise direction. So here, by the way, this is face A, this is B. Here we'll rotate it by clockwise. So this angle now is phi equals minus 34.5 degrees. Now what we'll see is that if you go by phi S1 in the clockwise direction, there will be a shear stress as well as a normal stress. So there is the shear stress is tau max, it's positive. So let's see. So a positive shear stress on the Mohr circle corresponds to a negative shear stress on the cube. So what we need to do is draw the negative shear stress here. So on face A, we'll have a negative shear stress. And there'll be a complement as shown. And then for the principal stress, we have sigma equals the center of the circle, which is minus 15. So everything there would be compression. So I would have compressive forces on face A, compressive forces on face B, and on the other side. So minus 15, tau max, which is 69.6. And then, of course, this angle is negative 34.5. This is phase A, phase B. And phase A, as you can see, has been turned clockwise by 34.5. Okay, so I'm not following my own rule. It just shouldn't be minus, it should just be 15. That's because I'm already showing it as compression in the figure. Okay, let's do one more question, and it's just a spin-off from this question. So I'm going to use the same cube element. So here's another example. I'm going to draw the same element with the same stresses. So 80, tension, tension. And then show the shear stress such that phase A, which is this, there is a negative shear, positive shear, and the shear is same as before, 25 MPa. Okay, so the question is as follows. One, find the stress when the cube element is rotated 30 degrees clockwise. And second, draw the corresponding stresses in the rotated configuration. That is, you need to draw this cube rotated by 30 degrees clockwise and then show the resulting stresses. So unless you do the first part, you can't do the second one. So we have already drawn the Mohr circle for this, and we sort of need to use that Mohr circle to figure out what the stress would be when the element is rotated by 30 degrees. So let's just quickly draw some parts of the Mohr circle as we'll need for this problem. You just borrow it from the previous figure. It's too cluttered. Let me take the other one. This is better. Okay, so what we need is really the center of the circle, and we need the principal stresses to draw this. So, okay, I also need one more quick piece of information here. I need to draw the point A because we're going to turn the face A by 30 degrees in the clockwise direction. So I'm going to show A here. A is from the previous figure, it's minus 80, 25. So join that. Okay, so now the question says, rotate face A or the cube by 30 degrees clockwise, which means that rotate face A by 30 degrees clockwise. So all I need to do is rotate face A on the Mohr circle by an angle twice what is on the element. So twice of 30 is 60. So I need to rotate this by 60 degrees. It turns out that 60 degrees is actually something like this. This is 60. If you remember, this was 21. So 60 plus 21 is 81. So this is about 9 degrees. So this is the point of interest now. We need to find the stress here. Once we find the stress at that point, we're pretty much done solving for the stress. So one way of solving this is to use pure trigonometry. We kind of know we kind of know what the radius is, and we know the point now. It's 60 degrees or 81 degrees from the x-axis. So we just use trig. So using trig, so let's just call the stress to be sigma and tau, unknown. And you can see that sigma is going to be the center minus 15. And then I need to find perhaps this distance. So this distance is going to be the radius of the Mohr circle times sine of 81 degrees. And then the other thing to be careful about is that since it's on the left side of 15, it should be negative. So the answer here is 15 minus r sine 81 degrees, which is minus 15 minus 69.6 sine 81 degrees. And that comes out to be minus 25.89 degrees. So next I need to find tau. And tau, as you can see, is just this distance. This is tau. So you can see that it is simply the radius times sine of this angle, just shown in red. So it is r times, oh, I think I did a mistake. Is this cos? It's cos. Yeah, I did a mistake. I have the answers right because I copied from my notes, but this is not sine. It is supposed to be cos. So please correct this. This is cosine 81 degrees, cosine 81 degrees, cosine 81 degrees. And this should be r sine 81 degrees. So r sine 81 degrees. And so that is equal to 68.78. This is not degrees, it's MPa. So that completes part one. The answers are these. And then the second part, we need to rotate the element by 30 degrees. So we just rotate the 30 degrees. So let's say that this is our original figure, original cube. we rotate by 30 degrees clockwise. So this was A, this is a new A, so let's call it A prime. And we need to show the stresses, which I found right now on this figure. So what we have to show is the normal and the shear stress. Now, sorry, the normal and the shear stress. Now, the issue here is that we only found stresses for A, right? We went A, we rotated it, we did not find stresses for B. So for every stress here, there's a complementary stress point here, and we need to find the stress right here. So sigma and tau. And so this is actually, turns out that the tau coordinate is not hard, it's just the negative of the previous one. So the sigma is going to be minus 15. So just like this will be plus r cosine of 81 degrees and then minus r sine of 81 degrees. So that will be, what I got is minus 4.1 degrees, sorry, minus 4.1 MPa, and then minus 68.78. So this is for phase B. So once I have that, now I'm ready to draw it on the figure. So this is A, this is B, this is my new B, this is my new A. Okay, so let's draw the stresses. So the stress on phase A is going to be sigma and tau, which I wrote down here. Sigma is minus 25.89. So I'll draw 25.89 and show it as compression. And then stress on B is 4.1, again compression. So I'll show it on phase B as compression. That's 4.1. And then the final thing is shear stress. Now, what we do here is we can pick a phase A or B. Let's say phase A. So phase A has stress of value equal to 68.78, which is positive. So a positive shear on the Mohr circle is a negative shear on the cube. So all I need to do is on phase A, show a negative shear. A negative shear on phase A is clockwise. And so I just draw it this way. And then you don't have to figure out anything for B because it's always complementary shear. So that is the shear stress, it's 68.78. Everything is in MPa. Okay, now I've only showed you how to do this with Mohr circle, right? Which is nice. If you like trigonometry, it probably is a good way to do it. But we also derive formulas for solving this. So let me show you how to do all these calculations only for this part using the formulas. And you'll see that we get the same answer. If you get the same answer, things are right. In fact, you can use this to check your answers. So let's do another way. That is, I'll solve part 1 using formulas. So this is plug and chug. There's nothing to really visualize and compute in terms of trig. So what we do is we write sigma x, sigma y, and tau xy. So if you remember sigma x, sigma y, the figure was 80, 50, and tau was like this. It was 25. So sigma x is clearly negative. Sigma y is 50. And tau xy Okay, we always write in terms of what we see on the cube, which is clockwise on face A. So it's 25 with a negative sign. Okay, so now we are ready to use the equations. The first equation for, and of course, we need to put phi equals minus 30 degrees, right? It's minus 30 because we want to find the stress at a element when rotated by 30 degrees clockwise. So clockwise is denoted with a negative sign. So sigma equals sigma x plus sigma y divided by 2 plus sigma x minus sigma y divided by 2 cosine 2 phi plus tau xy sine 2 phi. So plugging in all those values I put down there, you get minus 25.85. Okay, so just believe me now, or you can do the calculation yourself. And then if you put the formula for tau, we find the formula for tau. It is minus sigma x minus sigma y divided by 2 sine of 2 phi plus tau xy cosine of 2 phi. So again, plug the values. You get minus 68.79. So these are stresses at face A. How do we find the stresses at face B? What we need to do is we need to change the value for phi . Okay, so A is this, B is this. We rotated the element in this fashion. That's 30 degrees. So I need to find the corresponding angle for B. I'm trying to figure out how do I do that. So I have the same formula now. This formula phi only gives me the shear stress for face A when rotated by 30 degrees. I need to find a similar value, a value for face B. Once I get that value, all I need to do is sub in the same formula with the same sigma x, sigma y, and tau, and I will have an answer, a new answer for sigma and tau, and those will be my stresses at B. The question is, what is that phi for face B? You're only given the phi for face A. Can anybody find out? Can anybody think how you can get that? 90 plus.
Is it 60 degrees?
60 degrees. Okay, I have two answers. Okay, so the answer is 60 degrees. But I'm just kind of right now blanking on how I obtained it in my notes. So
Be a triangle, professor. When
be a triangle. I mean, this is 60 degrees, but the question is, why is it plus 60 and not minus 60? Maybe there's a hint in the Mohr circle. Let's see that. Okay, so this is A, that's B. So the angle between A and B is 180 degrees, right? So the angle between A and B is 180 degrees. And so that's on the Mohr circle. So it's going to be half of that if you take it for the cube. And that's the reasoning. So the way you can think of this is so we have two. So the answer is definitely 60 degrees. And here's the explanation. So we have on Mohr's circle, something really wrong about my computer today. It is running low on resources. Okay, let me raise this later on. So on Mohr circle, we have you can say 2 phi of A plus 2 phi of B is 180 degrees. And so phi of A plus phi of B is 90 degrees. And so if phi of B in this case is 90 minus 30. So it's 60 degrees. And so when you put 60 degrees, you get minus 4.1 MPa. And then tau equals minus 68.79 MPa. So this is using the formula and not relying on the Mohr circle. So some of you who don't want to use the formula, use the Mohr circle, can use the formula we derived. Okay, so you're almost out of time. So the plan is